set. For notes, we're going to be doing the last section in chapter 5, which is 5.5, inverse trigonometric functions on the graphs. And so now we've talked about all the functions, we're going to do all the inverses now. So the definition of the inverse sine. So inverse sine is given as this. So let me be very clear about this. So here we write, this means inverse sine of x. This sine of x inverse means 1 over sine of x. These are not the same thing. Sometimes in order to prevent that, we use the term arc sine to denote the inverse. So if the little -1 is on the sine, that means inverse sine, not 1 over sine of x. It has to be in parentheses for that. So please be clear about that. We use this as shorthand notation just because we use inverse sine all the time. This function has a domain between -1 and 1 because it does the exact opposite, and the range from -pi over 2 to pi over 2. And this will become clear why this is the range and domain once we draw it in a second. And what does it mean to be an inverse? Well, an inverse means it puts things back to where it found it. So here, if I had an inverse of x equals to y, that means sine of y was x. So if sine of y put something at x, it's going to take x, it's going to put it, the inverse of that is going to put it back. Okay. Alright, so let me draw this and then I'll get to the cancellation properties. So let me draw this. So we're going to start with the sine function real quick. So here's sine of x, and here we'll have this. We'll draw in our pi and our 2 pi, and we'll just draw this out. And then I'm actually going to go backwards a pi, just for fun. Alright, so we're going to go backwards a pi. Put in our halfway marks. It's going to go up from -1, or oops, it's going to go from 1, sorry, to -1. It's going to start at 0, going to come up, go down, go back, hit the negative, and come back in. So this is our sine of x. In fact, let's just draw it backwards for a little bit. We're going to come in back here, come up, and then go back in here. But if you remember from your 152, a function can only have an inverse if it's 1 to 1. That means it passes the horizontal line test. And notice this does not do well, right? Here I hit many, many, many points. And so what we're going to do is we're kind of restrict the domain to this, from here to here. And what is that? Well, that's pi over 2, minus pi over 2 to pi over 2. And so if we restrict the domain to these points, we'll get what we have here. It's like, and so if we restrict, then we can take the inverse of this function. So we just flip this over the x-axis. So remember, you can do this, flip over the x equals y-axis. And so here, when we draw in the inverse, we're going to be from minus pi over 2 to pi over 2. Oops, no, hold on. Let's be very clear about this. That's for sine. For this, then we're going to flip this, and so it's going to go from -1, so it's going to have our -1 here, it's going to have our +1 here, it's going to go all the way up to pi over 2, and all the way down to minus pi over 2, and then we can draw this in, comes in right here, goes in, goes up, and comes back in. And so here's our function. So here's our inverse function. So here, if I restrict this domain to this, and then I can take its inverse, so the output now becomes the input, and the input now becomes the output. And so now when we go back and look at all this, it'll make a lot more sense. Since sine can only go from -1 to 1, anything outside that we didn't come from a sine function. So the domain of the inverse sine has to be from -1 to 1. Its range, we're going to just chop it from here to here. So we just defined it to be from here to here in order to do it. Could we have defined it from pi over 2 to 3 pi over 2? Sure, right? I mean, you could have done that, but mathematicians a long time ago just defined it between, we'll just truncate the sine function this way. And so we showed this truncation that allows the inverse because it has to be a 1-to-1 function. So then we get our cancellation properties here. So if I take inverse sine of x, and then took the sine of x, well, that should give me x. But now we have to be very careful for what is allowed in its domain. So here, the domain of this is, I'm only allowed from -1 to 1 in the domain for inverse sine of x, and so then I have to restrict that this is true only between my domain for the sine of x, or inverse sine of x. Here I have sine of x. Inverse sine of x can input anything, right? But we need to restrict its domain to here in order for this inverse function to work. So it's from -pi/2 to pi/2. And then we take the inverse, but we'll get back the same function. Notice if you put sine of something higher in and then took its inverse, you wouldn't get back x. You'd get back the x which belongs in this area. Okay? So what do you need to know about all this? So let's sum it all up. There's an inverse function. So basically here, if you tell me the value of sine, I could tell you the angle. And so here you tell me what value of sine, I give you back the angle. And that's what's going on here. And so that's the point of why we use it. That way, if I knew the sine of x was something, I could figure out what the angle was. And so this has lots of useful properties. The domain of this is between -1 and 1 because the range of sine is between 1 and -1. Remember the domain and the range switch. And then here, in order to make this inversible, we truncate sine from here to here, and that way we get it from -pi/2 to pi/2. So let's actually crunch through some numbers. All right. So let's just do this. So sine of a half. A sine of a half, well, that's in our domain, right? So we can certainly, so sine of -1/2 is in our domain, so we can crunch through what that is. So we're going to ask ourselves, another way of asking is equal to, let's just say this is equal, let me go ahead and go back to blue. Let's go back to blue, is equal to x, right? Another way of asking this is saying the sine of x is equal to 1/2. So what must that have been, right? What must that have been? Well, the answer here is pi/6, right? So x equals pi/6. And so it's just asking the inverse question, right? And we can do the same here. Now, is there multiple things here which allow a half? Sure, there's infinitely many, but we want to be restricting to our domain here. And so what comes here would be pi/6. Again, so let's do this one. So here let's say this is equal to some y, and then we want to say sine of y equals a -1/2. Well, what sine of y equals a -1/2 where? Well, it equals -1/2 way over here, but do we want it way over here? No, so we're going to actually walk backwards for this one, right? And so in order to get the -1/2, we're going to take -pi/6. Okay? And so this is what y equals. And so here, so the sine of this is equal to this is equal to pi/6, and this is equal to -pi/6. Because notice where we normally grab it way up here, that's not going to work for us because we need to be between -pi/2 and pi/2. So let's pretend we have the inverse sine of 3/2. Well, that's not even allowed, right? What? Let's just mark this as z. This will say sine of z is equal to 3/2. Well, what angle gives that? Well, this is greater than 1, so that never occurs. So this is undefined, right? This is just undefined. Okay, so in this case, it's undefined, and we cannot do it. All right, let's do some more. All right, so let's pretend I wanted to find the inverse sine of a third. Well, how would I do this? Well, do I know a sine of an angle, say alpha, that equals a third? No. And so you literally just chunk this through a calculator. So you just plug it in a calculator. You'll just type in, you'll have like a sine 1/2 function, then you'll plug in a third, and then it'll roughly pump out an answer for you. So it roughly pumps out the answer of 0.33984. Okay. Here, let's pretend I want to take, so I'm going to take the inverse sine of a sine. So this is within my cancellation property. So I can just say, without thinking too much about this, right? I can just say, well, this is just pi/3, right? That's what it means to be an inverse. Wherever I put it, I'm putting it back. right? So this works out to be perfectly fine because of the cancellation property. However, this is outside of my cancellation property range, and so I'm actually going to have to do some mathematics here. So sine of 2 pi, so here we just take the inverse sine, and here if I find out what the sine of 2 pi over 3 is, if you remember, it is square root 3 over 2. And then here if I take the inverse sine of square root 3 over 2, that's going to give me the value of pi over 3, because I want to find out what angle gave me square root 3 over 2. That's between negative pi over 2 to pi over 2, and that, of course, is pi over 3. And so a lot of it's just messing with this and doing that. We can do all the same thing, and we're going to rebuild all of this for cosine. Oops, I did not put the co in there for cosine. So we're going to do all the inverse of cosine function right here. So the inverse of cosine looks like this, same as sine. Here we have the same domain. It's going to be from -1 to 1. But here our range here is from 0 to pi. And the reason is, let's go ahead and draw it first. Let's go ahead and draw this first. I did not switch any of this, did I? These should be cosines. Sorry about that. These should be cosines. And so let's draw them. Alright, so here, we'll go out to 2 pi, we'll go out to pi, we'll go out to our quarter marks. We're going to start from, go from -1 to 1. Here we'll start at 1, we'll come down to 0, and then we'll curve back in, we'll hit -1, and then we'll come back up and do this. Now notice, and this goes on and on, as you know, but here we're going to have to restrict this, and so we're going to restrict this much like we did for sine, but here we're going to grab the same kind of chunk from -1 to 1, but here we're going to do this from 0 to pi. So here we restrict it from 0 to pi, and then here I have my restricted cosine function, which allows me to draw my inverse cosine function. So this comes from -1 to 1, and then the values here are from this is pi over 2, this will be pi, so this is way up here at pi, and this is 0, so it's always above the graph. And so here I have from -1 to 1, I get from pi to pi over 2 to 0 at 1, okay? Alright, so now the rest of this should make a lot of sense. Here the inverse is what we said it before, it puts things back. We call this the arc cosine, or the arc cos, right? Here, notice that the domain here, because I can only take in between -1 and 1, because that's all x cosine can output, so the inverse can only input that. Here if I do this, I can get back exactly what I had, and then here, if I take cosine and then do the inverse, I get the exact same thing back as long as x is from 0 and pi. Alright, so let's do a couple of these. Alright, so what do we have here? Here we have inverse cosine of pi over 3/5 of this. So let's just do what we did last time. Say this equals that. That means cosine of x is equal to square root 3 over 2. Or is that true in the first set of pi? Well, that's true at x is equal to pi over 6, right? So that's what value gave that. So we just write here pi over 6. Here, this is between -1 and 1, so we can put it in. Do we know an angle that gives -5/7? No, so we just crunch this through a calculator. And as we crunch this through a calculator, we're going to get cosine of -5/7 is equal to approximately, we put in the approximate, 0.77519. Alright, let's do one more of these. Alright, so here, notice that this is outside of my range of my cancellation property, and so I'm actually going to have to compute this directly. So I'll have cosine of inverse. Cosine of 5 pi over 3 is 1/2. And then here, the inverse cosine of 1/2. What angle gives 1/2 between 0 and pi? Well, that's pi over 3. So this is just pi over 3. Okay. All right, let's go on to the next set. Now we can do all this again for the tangent function, and luckily this time I swapped tangents. So the inverse tangent function, well, the domain is all real numbers, right? Because tangent has a range of all real numbers, and so I can reverse any of that. But since it repeats itself, I'm going to restrict my I'm going to restrict it from minus pi over 2 to pi over 2. And let me explain why. Let's just draw in tangent real quick. So tangent from minus pi over 2 to pi over 2 comes in, goes out like this, and then these, of course, are asymptotic behavior. And then it repeats itself, right? It'll repeat on this side, it'll repeat on this side. But here, that'll break the horizontal line test. And so we're restricting it to just the first one period of it. So we're just restricting it here to this first period, like that. So if I ever do this, and then I just flip this on its side, here it's going to be from minus pi over 2. Oops, let me just do this back. Let me do this in blue. So this will be minus pi over 2 to pi over 2. Put in a dotted line. And then here it's 0. And then we'll go ahead and since this has infinite range, this has infinite range, and so it comes in like this, goes up, and comes back out. And so notice values I put in here will return the values I put in there. And so this is the inverse of that. Once we see this, makes a lot more sense. So the domain's all real numbers because here the range of tangents all real numbers, right? In order to, the range here, I'm going to restrict the domain from pi over 2 to, or minus pi over 2 to pi over 2. That way it's a 1-to-1 function, so just one value here. And so then I get this right here, and I can draw in the inverse. So inverse tangent of x, if I take the tangent of the inverse tangent, I'm going to get x for all real numbers, right? Now if I do that the other way, if I take tangent first, since I have to restrict the domain, it only works, the cancellation property only works first. From negative pi over 2 to pi over 2. Alright. So let's go over some of the values here. What is some of this? Alright, so here I have tangent of negative 1, so let's just say this is equal to x. That means tangent of x is equal to 1. Where is that true? In the interval between negative pi over 2 to, in this interval, from negative pi over 2 to pi over 2. So where is that true? That is true when x is equal to pi over 4. And so here, the answer here is pi over 4. Here, I have tangent. I want to know where tangent of, let's just use a different variable, y. What y is equal, what angle gives me square root 3 between the interval between negative pi over 2 to pi over 2. Remember, it must be in this interval. And the answer here, of course, is pi over 3. So y equals pi over 3. So we just go and plug that in. And then here, I have 20. Well, can I have what tangent equal to 20 here? Yeah, sure. I'm at some point here at 20, I can figure out what that angle is. Now, know what that is? No, you're just going to have to crunch it through a calculator. And you crunch it through a calculator, but this allows things much greater than 1, right? Much greater than 1. In fact, any real number, right? I can put 2,000 in there, and I still can crunch out a number. And here I'm going to get minus 1.52084. Okay? And so here we can take the inverse of all this. Now, there are these three are going to be what you're going to be using. You're going to be using inverse sine, inverse cosine, and then you're going to do the inverse tangent for 99% of all your uses. Do the other ones exist? Yes, let's quickly go over them. Well, these are far less common. They do appear from time to time. So here we have the inverse, well, less common than inverse sine, cosine, and cotangent functions. The inverse function secants do find their uses from time to time. So let's briefly just touch on them so you can see them. All right, so let's draw in our graphs. So let's draw in all our graphs first. So let's review how to do this. So here we're going to go from 0. We're going to go here to pi. I'm going to go here to 2 pi. Alright, and then here at the halfway marks, we'll draw those in. Alright, notice for secant is 1 over cosine. And so my zeros here are at pi over 2 and 3 pi over 2. So that's what we have. Here this goes from -1 to 1. And we just draw this in. And so here we go in and up, down and around, and then this, and then it goes back up. Okay, so here we drawn it in. But now we're going to restrict the domain. And we kind of restrict it a little bit strangely. We go from here to here, and we go from here to here. So that's where the domain is restricted. So here we're going to have our restricted domain is between 0 and, 0 over x over pi over 2, and then pi x 3 pi over 2. And then we'll go ahead and draw that in here. And so notice here between 0 and between -1 and 1, there's nothing, right? I have no values between -1 and 1 because no value of secant reaches it. So the inverse secant will have nothing in here. So that's not where it's in its domain. But then it'll come up here to, this is pi over 2. It comes up and goes out. And then here at pi, and then it goes to 3 pi over 2, and then it'll come up here and go out. And so this is what my inverse function looks like. Let's do the same thing again for the cosine, or the cosecant. Alright, so let's draw in cosecant. Cosecant is, as you remember, 1 over sine of x. Alright, so this is 1 over sine of x. And so let's go ahead and, so the zeros here are at 0. So here's one of my asymptotic lines. We'll draw in our pi. That's another 0. So we'll go ahead and draw that in. We have another 2 pi. We have another asymptotic line. Let's draw that in. Here we'll draw in our halfway marks. To help us draw this, we'll have 1 up here, -1 down here. So let's go ahead and draw this in. Comes in, hits that, goes up, comes in, hits the negative, and goes down. So where are we going to restrict this domain? In order to make this work, we're going to go from 0 to pi over 2 again. And then we're also going to go from pi to 3 pi, pi over 2. So this has the same domain as this one. So these are the same. So it's from 0 to x to pi over 2. And then pi less than or equal to x greater than 3 pi over 2. And so when we draw this in, once again between -1 and, make this all the same color, between -1 and 1, it's nothing. And so here at pi over 2, it comes, so here it starts and then it goes to 0 at this one. And then here, we draw a little dashed line right here at pi, and then goes up to 3 pi over 2, and then comes up and goes like this. If these seem a little bit strange, don't worry too much about them. These are uncommon, but it's a good thing for us to go over them. Cotangent may be a little bit more more common than inverse cosecant and inverse secant, just because it works out nicely. So here, let's draw one thing of cotangent. So we just come to pi, and it comes in. Comes in at pi over 2. So it comes in, goes out, comes back out, and then it repeats itself, right? So when we restrict the domain, we're just going to do it between 0 and pi. And so when we draw this, it'll just look like here at pi, it comes in, dot, 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 and so this will be my asymptotic line. So it comes in, to be pi over 2 because it goes through the 0, but this will go through 0. So it comes in, comes down, and then goes out forever. Okay? And so here we're restricting our domain between 0x and out here 0x and pi. These are asymptotic, so we should leave those out. Okay. Technically, I made a small little error. I should have left out one or two more things. I don't hit my asymptotes, so where I hit my asymptotes, I should have not had equal signs. So let me fix that real quick. So there's an asymptote here at 0, so I get rid of that. There's an asymptote here at pi, so I'm going to get rid of that one. Up here, there's an asymptote at pi over 2, so I'm going to not have that one. And here at 3 pi over 2, and I didn't have that one. Good, so here I just accidentally left it in here. Alright. So that's the end of these notes, and that's the end of chapter 5.